Hello and welcome to lesson 2.1. In this lesson we're going to talk about the relationship between secant lines and the graph of a function and how they relate to the tangent line to the graph of a function at a certain point. And we're going to see how these topics apply to finding the velocity of an object at an instant in time. So from our week 1 folder, this video is showing what's in this Desmos lesson here. So if you click this link, you'll be brought to this website, the student.desmos website, and I'd like you to enter your name when it prompts you to enter your name. At this page, it will prompt you to enter your name. So let's look at some pre-calculus things we're going to need to remember. You're going to need to remember function notation, how to represent a point on a graph in function notation, how to find the equation of a line from 2 points, and the different ways we can represent a function, graphically, symbolically, which means the formula, numerically, and verbally, which we're not going to talk about that much right now. And you need to remember the average rate of change of a function and remember how to calculate it. So this is reviewing all those concepts. So here's the function we're going to be working with a lot in this lesson, f of x equals x squared. Here's its graph. Here's how we represent the point 1, 1 on the function's graph with the function notation. The y-coordinate can be represented as f of the x-coordinate. So here you see that again. And here is that function represented numerically in a table. X is my independent variable, and f of x is my dependent variable. So you also need to remember what a secant line is. A secant line is a line that shares at least 2 points with the points on the graph of a function. When you have a secant line, if you have the points that it shares with the function, then you automatically have 2 points on the line. You can figure out the x and y coordinates of those points by using the x coordinate and then evaluating it at the function formula. And then you can get the slope and the equation of a line as you normally would. So let's look at this a little bit more. So here's the function f of x equals x squared. When x is 2, I know that f of 2 is 4. When x is 1, I know that f of 1 is 1. So the secant line to this graph at those 2 points can be found, the equation can be found by knowing that these 2 points line that line and then just finding this equation of the line as I normally would. I get the slope, which is the change in y over the change in x. And then I'm going to use one of those points on the line to figure out the equation. So the average rate of change of a function is just a generalization of finding the slope of a secant line between any points. So here I have the point A, f of A, and B, f of B, so I'm just generalizing. And the slope of a secant line between those 2 points on a line is just going to be the change in the y values over the change in the x values, and you should remember this as the average rate of change formula from pre-calculus. So why do we care about secant lines? Because what we really care about is the slope of the tangent line to a function. So a tangent line touches the graph of a function at one point in some neighborhood. So what we're interested in here is at the point 1, 1. This red line is the tangent line, and it touches f of x equals x squared at just this one point. So we're going to be using secant lines to approximate the tangent line to a function at a point. So what we're going to be doing is moving a point closer and closer to a particular point on the line, in this case 1, 1. So in this case my other point is the point 2.5, f of 2.5. So we can figure out the slope of that line by evaluating the function f of x equals x squared at 2.5, which gives me 6.25. And then I figure out the slope as normal. Change in y is 6.25 over 1. Change in x is 2.5 minus 1. Sorry, before I meant 6.25 minus 1 over 2.5 minus 1. And that's going to give me a slope of 3.5. And notice that the slope of my tangent line is 2. And we'll talk later on how to get that. Now I have another point that's closer to 1, 1. So now it's at 2, f of 2. And if we figure out the slope of this secant line, we're going to see it's 3. So it's gotten a little bit closer from 3.5 to 3. Now my secant line goes from the point 1.5, f of 1.5, to 1, 1. So figuring out the slope of this green dotted secant line, it's 2.5. So now we're a little closer to that slope of 2. And now if I get even a closer point, when x is 1.25, if we figure out the slope of this purple line, now it's 2.25. So you can see that the closer I get this other point to the point I'm interested in, 1, 1, the better approximation the slope of the secant line is to the slope of the tangent line. So the slope of the tangent line is called the instantaneous rate of change, whereas the slope of the secant lines were the average rate of change. So thinking of instantaneous rate of change is not always intuitive, because what's changing? X isn't changing anymore if I'm just at one point. But this is the concept of changing an instantaneous velocity or an instantaneous rate of change is the slope of the tangent line to a function. We'll talk about that a little bit more in a minute. So now let's look at how the book refers to all this. So I'm going to click over here to the ebook, which you can access from WebAssign. So if you go to our home page in WebAssign and you click down here, it'll bring you to the ebook. And the ebook has this example, and so it shows the point P is the one that we're interested in, 1, 1, and Q is the other point. So it refers to the slope of that secant line as m sub pq. So I've adopted that terminology here. So you have homework questions that's going to ask you how to find the equation of a secant line. And remember, it's just finding the slope, and you're going to have 2 points on the line, so you can find the slope, and then remembering the point-slope form of a line. And I'll leave answering these questions to you. So if we look at this in real time, I'm going to move my point Q over here, and here's my point P, and we're approaching, Q's approaching P. Up here's the slope of the secant, and here is the equation of the secant as Q changes. And notice that that slope is getting smaller and smaller. It's approaching the slope of the tangent, which we know is 2. So what happens when P finally does reach Q? Then I have this undefined slope, right? It no longer makes sense. This definition or this formula for slope no longer makes sense because my x coordinates are the same and I can't divide by 0. So this is an example of the limiting value of the slope the slope of the secant lines were approaching the slope of the tangent line. The slope of that tangent line is the limiting value of the slope of the secant lines as I move Q closer and closer to P. So you've seen the concept of a limit before in pre-calculus. Think of rational functions in particular. A function that approaches a vertical asymptote as x gets closer and closer to where that vertical asymptote is, or a hole. As x gets closer and closer to that x value where the hole occurred, it's approaching the y value where that hole is, but it doesn't necessarily reach that y value, but you can get as close as you want. That's the same concept. I'm getting as close as I want to this point P, and the Desmos slope being defined, it's only in units of hundredths, but I can always get closer and closer and closer, but that limit is going to be the slope of the tangent line. So there's a concept of approaching from the right and the left, and you'll see this especially in tables in the homework. So we say that this point Q is approaching P from the right if the x values are to the right of 1 and getting smaller as they approach 1, like this, graphically. And then if you look at it as a table, you'll see that the x values start out bigger and they get smaller as they approach 1, and the slopes are bigger and they get smaller as they approach the slope of the tangent. And here it's approaching 1, 1 from the left, and you'll see that the x values are smaller and they're getting larger as they approach 1, and the slope values are smaller and they're getting larger as they approach 2. In the next video, we're going to look at instantaneous velocity and how all that relates to what we've just looked at with the secant and the tangent lines.